So today we're very happy to have Mark van Raamsdonk. So Mark did his PhD at Princeton and then a postdoc at Stanford when I was a graduate student there. So I've known him for a very long time. And then from Stanford moved to University of British Columbia as faculty and has been there ever since. So in my opinion, one of the most exciting and intriguing discoveries that's come out of theoretical physics, high energy theoretical physics in the last decade, has been the connection between quantum entanglement, quantum information, and gravity. So Mark has been one of the leaders in investigating that, and he's going to tell us today how we can deduce really basic things about gravity, things like the inverse square law of Newton's law of gravity, from quantum information, from properties of quantum entanglement. And just to be clear, this is not saying that gravity is a quantum phenomenon. There's no h-bar in Newton's law. But rather that there exists a dual description. There exists a description that we think is equivalent in all respects where classical gravity can be described this way in terms of a different set of degrees of freedom. So this is really an interesting line of work. Yeah, very happy to have it. So thanks, Mark.
Okay. Okay, so thanks for the invitation and the opportunity to talk here. And indeed, I find this whole convergence between quantum information ideas and quantum gravity to be really exciting. I got into it and it just turned out to be sort of even more exciting at every stage than I could have hoped. So I want to kind of share with you just some of the very basic aspects of this today. And so the background for this is kind of our quest to understand how to fit gravity into the framework of quantum mechanics. Kind of is what got me into this area. This is sort of a big challenge for theoretical physics. And why do we want to do that? Gravity is usually a physics that has to do with long distances. Quantum mechanics, usually we care about it when we're thinking about short distance physics. But there are certain situations where you really need to have both of these things. One of them is to really understand the physics of black holes. The other one would be the physics of the very early universe, to say what is the Big Bang. So there are really situations in our universe, present and past, where we would need both of these things to come together for a full theoretical understanding. Okay. Let me just start, since this is a general talk, to make it clear when I'm talking about gravity. What I'm talking about is Einstein's picture of gravity, where gravity is like the dynamics of space-time geometry, how that interacts with, how that's curved by energy and mass, and so we have this dynamics that explains gravitational physics, and all of that is summarized by Einstein's famous equation, which says that some measure of the curvature of space-time is equated with some measure of how much energy and energy density and momentum density and matter you have at that point. Okay, so that's like the classical version. That's our best classical theory of gravity, and it does great at solar system scales and all the way up to understanding the evolution of the universe. For the reasons I mentioned, we'd like to promote this to a quantum theory like we did with electrodynamics and eventually the Standard Model. But that has turned out to be a very difficult, kind of decades-long quest. I'm going to skip over many of the details of that and mention that in 1997, coming out of string theory, we had what I'd say is the most important progress in this direction. A really revolutionary and remarkable idea by Maldacena, which is now known as the ABSCFT correspondence. And that is basically the statement that at least certain examples of fully fledged quantum mechanical theories of gravity are actually entirely equivalent as physical systems to much more ordinary pedestrian non-gravitational systems. So I'd say prior to this, we didn't even have a full, so we didn't even have a full definition of any theory of quantum gravity. And then this correspondence tells us that, in fact, there's certain normal quantum systems without gravity that you can write down that in some sense serve as a complete definition of the gravity theories. And I'm going to tell you more how that works. So that was like a little more than 20 years ago. It wasn't really obvious how it worked. So there was a statement. People tried to do lots of checks. I don't know, there's like 15,000 papers now, many of which are checking this correspondence and showing that it seems to be consistent. But it really, for a long time, I don't think we had any good answers to how does space-time really emerge from this ordinary physical system, or why is there gravitational physics there in something that doesn't look like a gravitational system? And I guess maybe part of the reason why we had difficulty answering these really fundamental questions about this correspondence is that we were looking at the physics of this system in the wrong way. These kind of ordinary systems are like quantum field theories, are the kinds of theories that particle physicists and condensed matter physicists use. And the kinds of questions we were asking about those theories were things like what are the correlation functions, and how do these correlation functions relate to quantities on the gravity side? Okay. So it turns out that in understanding the correspondence more fundamentally, it turns out in some ways it's better to ask the kinds of questions that quantum information theory people would ask, rather than what are the correlation functions of specific fields, to actually think about how much is this part of the system entangled with this part of the system. These more general and universal quantum mechanics questions turn out to be more closely related to universal things that we might want to understand on the gravity side. Okay, so that's been the big progress I'd seen in the last 10 years. And so I think we now understand this whole thing a lot better, and this is opening the doors to understanding things about black holes, and hopefully we're getting towards maybe being able to apply it to the Big Bang or cosmology.
Sorry.
That's okay. Okay, so I want to start with a review of what is this ABSCFT correspondence, and it's really bizarre. So I said, it's that these theories of quantum gravity are equivalent to more or less ordinary quantum systems. And so you should have in your mind a quantum system that could literally be sitting in a box. And if you opened the box, inside the box, there would be like this ball, just like a shell of matter. It could be a ball of copper, just a hollow ball, so it's just a spherical shell. But it's not you do some investigation, it's not copper, it's just some more exotic material. But this is the kind of system that we're talking about, just sort of a system with a fixed geometry. It can have excitations, waves propagating on the surface. You can have energy. It's more or less an ordinary kind of quantum system that you could imagine studying in the lab. Okay. But apparently, this guy has all of the physics of quantum gravity, so it somehow is equivalent to the physics of planets and black holes and whatever you want in some universe with infinite volume. So how does that work? Well, fortunately, we have instructions there in the box. So I'll tell you a little bit. So we open the instruction manual, and so the idea is that here's our ball system. It's described by its time evolution is described by the Schrödinger equation. We can write down the Hamiltonian, so we know exactly what this system is. You can calculate. In principle, you could calculate anything you want by putting this on an in-principle computer. And the idea is that somehow every state of this thing is encoding some particular state of our gravitational system. I mean, I kind of like to think of this as being like a quantum computer chip that's encoding the gravitational physics, like a computer chip would be encoding what's on your screen in the computer. So there's some kind of a dictionary that allows you to translate this thing to what's over here. And so we know, even originally we knew some elements in this dictionary. So we understood that if you took this ball and you cooled it down to absolute zero, so it's in the vacuum state, that this would be encoding just a big empty space-time. In the simplest example, it's a very particular kind of space-time called anti-de Sitter space. And so what that is just a space. It's a very symmetrical, homogeneous, and isotropic space-time where the curvature of space is negative. Okay, so it's kind of the opposite of, you could have flat space or you could have a positively curved sphere, but then you can have this negative curvature. A way to picture that is to take this Escher drawing and imagine stretching it out so all of the angels and demons were the same size. So you could do that, and then you would get this negatively curved space, and locally that would look a little bit like this. Okay. But it's an infinite distance from here to the end because there's an infinite number of these demons. Okay. The details of this won't be too important for the talk. Okay. But so for now, the idea is if you have the vacuum state over here, that's describing in some way completely empty space with a negative curvature. Okay. Well, now what could we do? Starting with that situation, we might add a little bit of energy. So you could come along in your lab and tap that thing with a hammer to give a little bit of energy to your system. On the gravity side, that state we understand would now be some perturbation of the vacuum state. And you can think of that as being a perturbation of empty ADS space. So there could be now a few gravitational waves propagating on an otherwise empty space. But you could also add more energy to this system. So here's a situation where I've now added a bunch of energy over here and some energy over here, and there'll be some interesting dynamics. And so the idea would be, well, for the right choice of state here, well, that could correspond to some very interesting gravitational physics, like two black holes orbiting each other and merging and emitting gravitational waves. Okay, so there should be, given this picture on the gravity side, there should be some set of quantum states over here that would be encoding that physics. Okay, but yeah, what is this dictionary? So if someone just gives me, we know what this system is, we know the Hamiltonian and everything. If someone gives me a quantum state and I'm allowed to calculate anything I want, how can I take that and figure out what is the space-time that's being encoded? What's the gravity picture? And so that's one big question. And then the other question is, well, why, what about the physics of this non-gravitational physics, it gives rise to Einstein's equations and all of the interesting black hole phenomenology or other gravitational phenomenology. How is all of that physics that we're familiar with encoded in this more ordinary physics? Okay. And these questions were not at all answered when the correspondence was originally proposed. Okay, but we've made a lot of progress. Okay. So I want to start by talking about this code. How do you decode the quantum state to figure out the space-time geometry? And the answer, or one answer to that, actually had its origins back in the 1970s with the work of Bekenstein and Hawking and others. And so I'll just remind you about some of that work. They were studying black holes originally in classical gravity, and they realized that the dynamics of black hole horizons, and specifically the area of these black hole horizons, actually is a lot like the physics of entropy in thermodynamics. Okay, and in fact, there are precise laws that you can derive using general relativity that look like the laws of thermodynamics. So, for example, the area of a black hole horizon under various dynamical processes can be shown always to increase. There's something like the first law of thermodynamics where entropy is replaced by area and energy is replaced by the mass of the black hole, and temperature is replaced by a quantity that measures, it's called surface gravity. It measures like the gravity of the horizon. Okay. So that was some interesting observation that there seems to be some connection between classical black hole physics and thermodynamics, but it really wasn't understood. Like why should there be such a connection? Okay. But now we can jump ahead to this particular way of defining a theory of gravity, where you know, we might have a black hole in this side, and then so I was sort of showing you that adding a little bit of energy on this side adds a little bit of energy on this side, and adding a lot of energy on this side adds a lot of energy on this side. And so it turns out like a large black hole in this ABSCFT correspondence is just what you get when you add a lot of energy to your ball. So you just take this thing, put it in an oven, bring it to some very high temperature. The R is the radius of the ball. That's sort of the scale that we need to come up to. So if T is significantly greater than 1 over R, then this guy encodes some black hole. Okay, the state here corresponds to a black hole state there. And if you take this sort of more fundamental viewpoint about, okay, what is this in I guess this more fundamental description, it actually completely explains these results of Bekenstein and Hawking and others in the 70s. Okay. So if there's an underlying view where a black hole state is really being described by some thermal state of this kind of auxiliary system of like these underlying degrees of freedom, and if furthermore, part of the dictionary that goes between these says that the area of that guy is actually the entropy of this guy, then it immediately follows that the black hole area, horizon area, should obey laws of thermodynamics. Because this is just an ordinary thermodynamic system. It must obey the first law of thermodynamics, and it must obey the second law of thermodynamics. And so if in this correspondence the entropy here matches the horizon area here, and say that the energy here matches the mass over here, then it would follow immediately that black hole areas obey laws of thermodynamics, or obey parallel laws to the laws of thermodynamics. Okay, so that's just kind of accepting that there is this correspondence, that black holes are related to high energy states here, and that that entropy here maps to area there. Then we can explain those results. Okay, so we can think of those results as suggesting this element of the dictionary. Question?
Yeah, there's something confusing to me there,
Yeah.
because the fact that entropy increases in classical thermodynamics relates to the initial conditions of the universe. The initial conditions of the universe are not low entropy. Entropy doesn't increase. It only increases in the case that the early point is that the initial conditions are low entropy. But the Bekenstein and Hawking result is very classically guaranteed, kind of independent of initial conditions.
No, I mean, it depends on initial conditions, because you can time reverse it, right? So
Yeah.
it depends on the fact that you are assuming something on the past and on the future.
I see. So even in the black hole
Yeah.
area increase, you could change the initial conditions and then the area of the black
Yeah,
hole
there could be
would
very finely
decrease.
tuned states where you.
I see. Okay,
violate.
so it is the same
Yeah.
same conditions. Interesting.
Okay. Right. So I was saying, what we did here was make this observation about black hole physics apparently being connected to thermodynamics, and that can be explained if it's true that the horizon area in this gravity picture is actually an entropy in the other picture. Okay. So that's a, you know, it's not the full dictionary, but if you accept that, you now have a way to learn about the geometry over here. That's one element of the dictionary. If you give me a CFT state there, I can compute its entropy, and then from that I can deduce that there's a horizon in the dual space-time, and I can figure out what its area is. I can't yet figure out what the whole space-time looks like. Okay, but it turns out there's a generalization of this idea of this connection between entropy and horizon areas that will get us a lot of the dictionary and allow us to do this decoding. Okay. And so to talk about this generalization, I want to talk a little bit more about entropy and remind you just a few things about how that can be generalized to entropies of subsystems of quantum systems. Okay, so I'll start by just reminding you that one way to define the entropy in this simple case where we're just talking about thermodynamics is to say that, well, the thermal state here, when I have this ball at a certain temperature, that's really fundamentally described by this canonical ensemble where we have certain states with probabilities proportional to these Boltzmann weights. And then if I want to calculate the entropy, I can write a formula for that directly in terms of the probabilities. Okay, so this is just the standard formula for entropy in terms of the probabilities in an ensemble. And that works for the canonical ensemble or microcanonical ensemble. It's just a general formula for entropy in terms of ensemble. Okay. Now I want to think about just a general quantum system. I'm no longer necessarily thinking about some thermal state. It could be any state. My system, I've just drawn a bunch of spins. Could be anything. So let's imagine that we have a state of all these spins. And what I want to do is think about the state of a subsystem. Okay, so what I want to do is show you that this notion of entropy is something that is very natural to associate to actually any subsystem of any quantum state. So when you have a quantum state of say, a bunch of spins like that, a natural thing that you might want to do is represent the information about a subsystem. And in classical physics, you could just say what are the orientation of the spins in the subsystem. In quantum mechanics, you might think, well, given a state of that whole system, I could just write down some particular state of two spins, and for some choices of these coefficients, that would be the state of the subsystem. But actually, that's impossible. That's one of the main differences between classical physics and quantum physics. There is generally no state of this form, no pure quantum state, where if I did measurements on the spins in this state, they would match with measurements on the spins on these two spins in this full state. Okay. So in the context of a larger system, this system of two spins can exist in more general states than these. The general way that you can describe the state of this subsystem is using an ensemble. Okay, so you actually have to, if I want to keep track of what is the state of those two spins in this large system, what I need to do is say, well, there's a set of possible quantum states. These are orthogonal states of this form. And then there's some set of probabilities. Okay. And now if I were to calculate anything relevant to those two spins for this set of states and take the average using those probabilities, I would match the answer to the question about those spins in this larger system. Okay. So given the large system, then I can, given any subsystem, I can always find an ensemble like this which captures all of the information about the subsystem. That's equivalent to the idea of a density matrix, but for me it's going to be more useful to think about the ensemble. Okay. Great. Well, so now this ensemble is just a list of orthogonal states with a list of probabilities, and it's now natural. It looks just like the thermal ensemble or the microcanonical ensemble. There's sort of a classical uncertainty about which precise pure state these spins are in. And so it's sort of natural to also associate an entropy to that ensemble that describes the subsystem. And we use just the same formula. Okay, and so this is the idea of subsystem entropy in quantum systems. Take any quantum system, take any subsystem, and there's an entropy I can associate with that subsystem. This entropy is also called entanglement entropy because it quantifies how much the subsystem is entangled with its environment. Let me do a very simple example, the one that is commonly discussed when we talk about entanglement. So let's think of just, now the full system is just 2 spins, and my subsystem is going to be 1 spin. Okay. And so in this example, if I ask, what is the state of the first spin? Well, it's just this. And I don't need an ensemble, but I could describe it using an ensemble where it's up with probability 1. And I calculate the entropy of that, and it's just 0 because I just have p equals 1. Okay. So this system is not entangled. Here's a system, and here's a system which is entangled. If I want to describe what is the state of the first spin in this system, then the answer to that is that this first spin is in an ensemble where it's up with probability 1/2 and down with probability 1/2. If I plug that into the formula here, then I get an entropy of log 2. Okay. And so the entropy here is a way to quantify how much entanglement is there. I mean, we would say, well, this is not entangled because it can be written as a product state, or the state of this subsystem is pure. This is entangled. But if you want to actually quantify how entangled is a subsystem with the rest, then you can use this notion of entropy. If I had something that's 0.99 times that plus 0.01 times this, you'd have a lower it would still be entangled, but you'd have a lower entanglement entropy. Okay, so that's the main technical thing and that we want to use going forward. The summary is just, given any quantum state with a subsystem, we can associate an entropy to that subsystem. Okay. All right, so back to ABSCFT, we had this idea that the entropy of the entire ordinary quantum system corresponded to the area, to some area on the gravity side, which was the area of a black hole horizon. Now we've just learned that there's all sorts of subsystem entropies that we could also compute given the state of this system. So for example, we could compute an entropy associated with just that part of the system. What these guys proposed about 10 years ago, Ryo and Takenagi, is that all of those entropies have a geometrical interpretation. So while the entire entropy of the system corresponds to the area of some black hole horizon, in this case, they said, well, that this entropy corresponds to some other area in the geometry. And the entropy of this part of the system would correspond to some other area. And furthermore, that it's not important that we started with a thermal state. So in my definition of the subsystem entropy, the whole thing didn't have to be thermal at all. So Ryo and Takenagi also said, well, you could just have any state of the CFT. It doesn't have to have a big black hole. You could have like a couple of smaller black holes or no black holes at all. They said there's still a correspondence between entropies of subsystems and areas in the gravity picture. Okay. And so let me just now tell you what that correspondence is. Okay, so so Ryo and Takenagi said, let's pick a subsystem. Here's a ball-shaped region on one part of my sphere. Okay, so you can compute the entropy of that. What does it correspond to on the gravity side? On the gravity side, we've got some space-time, which you can imagine is like in the interior of the celestial sphere. And we want to figure out what is the geometry inside. Oops. So this could be just flat and empty, or it could be curved. So given any geometry, there's certain special surfaces that extremize the area. They're like the higher dimensional analog of minimal length curves in a space-time. So what this surface is, it's the surface whose boundary on this kind of celestial sphere at infinity, whose boundary is this region that's analogous to that region there. But in the middle, it's allowed to do anything it wants. And out of all those possible surfaces, there's going to be one that has the least area. Okay. And this was the proposal about how to interpret the subsystem entropy of this CFT state. You calculate that, and then that corresponds to the area of this particular surface in the corresponding geometry.
Mark, are we doing classical or quantum gravity here? Because this area of certain
Yeah.
surface,
So
that's intrinsically classical.
that's right. So this is here. So far, I'm just taking into account the classical effects on the gravity side. If we get more deep into the story, there are corrections to this that take into account some quantum properties. But right now, sort of to the leading order of approximation, the correspondence just says that this entropy equals that area, okay, which is strange because that's a very quantum thing. It's measuring entanglement. This is an entirely classical thing from the gravity side. Okay. Okay. So that turns out to be very powerful. If that's true, it actually gives us a way to crack this code that I was talking about. So to start from a state and figure out what the geometry is. Because what I can do now, if you give me the state of my ordinary quantum system here, I can think of all sorts of possible subsystems. Basically, any subset of the area of that sphere gives me a subsystem, and I can compute the entanglement entropy or the subsystem entropy for all of those. And then I can ask, is there a geometry that I can find where the areas of all these minimal area surfaces match with all those entropies I just computed? Okay. That turns out to be a highly over-constrained problem. Okay. If I take a ball of copper in some random state and I compute the entropy of all the different subsystems of that copper, and then I try to find a geometry where the areas in that geometry like match the answers that I got by computing the entropies of these regions of my copper, I would not be able to find any geometry that does that. I mean, the reason is that this entropy as a function of the subsystems of a sphere, that's a function on a much larger space than just like a metric function in 4 dimensions. Yeah.
How does this jive with the fact that you can know everything about a system and nothing about its subsystems? In other words, how do you know anything about the subsystems?
So here, I mean, if I have I mean, this would be assuming I have complete information about the whole system. So in this case, given psi, I can compute the density matrix for all the subsystems, and I can compute the entropy of all those density matrices. Okay, so in this case, this would be enough information to
But
calculate all
you would
those.
have to have information on the subsystems.
Well, when I say psi here, I mean the quantum state of the full, of all of the degrees of freedom. So that, that would include the full information about the subsystems. Okay. Okay. So the point here was that, if you tried to solve this problem mathematically for just some arbitrary system like a ball of copper, you would compute all these entanglement entropies, and you would not be able to find a geometry whose areas captured all of those things. And so if there is such a geometry, then you certainly have enough information to find it. Okay. So I guess mathematically speaking, this is a statement that, given, if I give you the areas of all these extremal surfaces with certain boundary conditions, that's enough to kind of reconstruct the metric of that space. More precisely, it's just a part of the metric that is covered by such surfaces. So there could be regions of the space-time where none of these surfaces touch, and then I can't necessarily reconstruct those parts of the space-time. Okay. But it goes a long way to reconstructing the metric. It goes a long way to cracking this code. The mysterious part, so behind black hole horizons actually turn out to be a really challenging part. To understand the physics behind black hole horizons from CFTs, sometimes you have to do something more than that. Okay, so it's amazing. We sort of cracked the code, and in this way of doing it, the thing we had to ask about was actually something very quantum. It was the quantitative measure of entanglement between every subsystem and the rest, and by using that information, we could actually deduce the classical space-time geometry. So you can say that the space-time geometry, in that sense, it's like a geometrical manifestation of the entanglement structure of that quantum system.
And is there a one-to-one correspondence
So-
between the QFT
Yeah.
and the gravity?
Yeah, so that's a good question. So it seems that the amount of information that you need to reconstruct the geometry is quite a bit smaller than the amount of information that's contained in the quantum state. And so but that's sort of natural, because on this side it's not just a geometry that would be there in that physical system. So in a full theory of quantum gravity, we would have a geometry, and then on top of that, you would also have various quantum fields in their own quantum states. And so it's natural that we shouldn't need to use all of the information here to reconstruct that, just a small part. Okay. All right, so you can take this, I mean, there's sort of a more profound lesson that all of this is suggesting. And the example that I think most strongly suggests that, this was particularly inspiring to me when I was thinking about these things 10 years ago. The most inspiring example is this one of Maldacena, who in 2001, before all of this, wrote a paper where he was basically interested in the following question. We talked about how black holes correspond to high energy or thermal states in the CFT. He was interested in how to what the corresponding state over here would be for a particular kind of black hole solution that you learn about in general relativity classes. So there's a very nice black hole solution of Einstein's equations where it's like taking the black hole and then extending it as much as you possibly can to get as complete of a geometry as you can. So this is called the Kruskal extension of the black hole geometry. It's a space-time that actually ends up having two asymptotic regions, each of which has a black hole, but then the black holes are connected behind the horizon. So there's like a wormhole between these two things. And sometimes this just seems like a total abstraction. It probably has nothing to do with black holes that form from collapse. But Maldacena was interested in, is there some, given this more fundamental way of describing gravity, is there some way we can describe that sort of interesting two-sided black hole space-time? And so he made a proposal, which is that, that seems like there should be two different copies of our ball system, because you have these two black holes in separate spacetimes. So there should be sort of two thermal states. But he said, well, maybe there's this very special state where each one of these serves as the heat bath for the other one. Okay, so when we have a thermal state, it's like a system, and then that's, in the quantum language, entangled with a heat bath, and then the subsystem is in the thermal ensemble. Okay, so there's a very special kind of quantum state you could write where you have two equivalent subsystems. Each one of them is in a thermal state, and then the full state is this pure state. Okay, so it's just a particular way of entangling these two systems so that each one looks thermal. And so Maldacena said, well, this picture with entanglement between these two, it's kind of a lot like this picture, and proposed that these two, that this was the fundamental way that you could describe this in the ABSCFT correspondence. You have these two CFTs now, you entangle them in some special way, and then that corresponds to this one space-time which is connected behind the black hole horizon. And so that seemed really exciting to me and other people, because these guys are not interacting at all. The only thing that relates these in any way is the fact that their quantum states are entangled with each other. And yet on this side, you have this physical classical bridge between two parts of space. And so we've seen that entanglement can be used to kind of decode what the geometry of space-time is But this sort of example suggests that maybe the entanglement is actually responsible for there being space-time at all. That, for having entanglement here actually just, it connects two parts of space with some geometry that otherwise wouldn't have existed at all. And so you can sort of try to explore that more. One of the things that you could imagine doing is starting from now just ordinary empty space. Start with a vacuum state of our ball system. Quantum field theory systems actually have a lot of entanglement between the different degrees of freedom, even when you're in the vacuum state. Okay, so if I cool that down to absolute zero, the fields on this side are entangled with the fields on that side, or the degrees of freedom. But I'm allowed to consider any state of this theory that I want, so I can imagine decreasing the entanglement between two sides of the sphere. I make some arbitrary division on this sphere, and then I just start decreasing the entanglement on the two sides. And I can ask, well, what happens then to the gravity side? And so one can use our dictionary and try to answer the question of what happens if I start with empty space-time, but now on the ordinary quantum mechanics side, I just remove entanglement. It costs me energy to do that, actually, because this is the lowest energy state. But if I do it, and I apply the dictionary, what I find is that sort of big empty space-time, as I remove the entanglement, it starts pulling itself apart. And eventually it just splits into two pieces. Like I took a wad of gum and stretched it out, and then it snapped. So the entanglement, removing the entanglement between two halves of the sphere, it pinches the space-time into two pieces. And you can imagine doing that, now dividing your space further and just trying to remove all the entanglement between degrees of freedom and nearby degrees of freedom. And you follow the dictionary, and it seems to suggest that that nice classical empty space-time that you started with just fragments into infinitely many kind of little pieces, and you don't really have a nice space-time picture in the end.
So when you describe it as following the dictionary, is it just you're saying, well, logically that's how it would have to work? Or can you actually calculate something to demonstrate?
Yeah, you can calculate. I mean, you can calculate in specific examples. You can find some one-parameter family of quantum states where the entanglement on the two sides is decreasing. And at least in the specific examples, we can say exactly what is that geometry, and you could measure distances and areas and everything. So I'm just drawing pictures here, but yeah, there's calculations that you do. Okay, so that suggests sort of some fairly profound sounding slogans that, you know, maybe in the way that this description of gravity works, this fundamental description of quantum gravity, the classical space-time geometry seems to emerge because the underlying quantum system has entangled all these degrees of freedom together. And if you remove that entanglement, maybe your picture of classical space-time goes away completely. Okay. Good. Okay. So the summary so far is that we have understood in this particular way of doing quantum gravity, where you use a more ordinary quantum system as the fundamental definition, and then extract the information about gravity through this kind of code, it seems like this space-time geometry is more or less directly a picture of the entanglement structure in the quantum state. Okay. And now we can ask, well, what can you do with that? So Einstein gravity is more than just a picture, more than just the statement that space-time can be curved. There are these detailed dynamical equations for how that curvature evolves and how the space-time geometry interacts with the matter that's in the space-time. Can some of that be deduced or understood in terms of physics of entanglement? Okay. And so, fortunately, there's been a community of people in quantum information theory that have been working for many years, understanding lots of things about entanglement, and they've written down all sorts of interesting constraints and formulas that entanglement would have to obey, and they didn't ever think about gravity, or that it could one day be relevant to gravity. But now we can exploit all of their work and try to see if many of the things that people already knew about entanglement physics translate into some useful things about gravity. Let me give you a simple example. So we've been talking about entanglement of various subsystems of a spherical system. So there's some things you can prove for any quantum system mathematically which relate entanglement entropies for subsystems. One of them is called subadditivity. If I think of a subsystem which is the union of A and B, then the entropy of entropy of A plus the entropy of B is greater than or equal to the entropy of the subsystem. We're used to think of entropy as being extensive, but these quantum entropies that I defined earlier are not necessarily extensive. However, they do obey an inequality rather than an equality. Okay? So you cannot find a quantum state where this is violated. A more complicated one is this. This is called strong subadditivity, and there's a whole list of these things. Now, let's interpret this on the gravity side. Okay, so if it's not possible to find a quantum state where this is violated, what that means is if geometries fundamentally are coming from these quantum states, then it should be not possible to find some consistent geometry in your gravitational theory whose areas violate this. Okay, so you can translate these, because we have a translation between entropies and areas, you can translate these constraints to constraints on which spacetimes are allowed and which spacetimes are not allowed. Let me give you a really simple example.
So those are constraints on the classical spacetime.
Yeah, these are just constraints on the classical spacetimes. Okay.
So they don't constrain the quantum theory, or does it?
You can come up with constraints on, you can deal with these sort of things quantum mechanically as well, and you can get constraints that take into account the quantum physics on the gravity side. But for this talk, I'm going to focus on the classical physics. Okay. All right, so let me tell you about one constraint. The very first constraint that you ever learned about entropy was the first law of thermodynamics. You learned that if you start with a thermal state and then you vary that to a nearby thermal state, then the change in entropy is related to the change in energy through this relation. What I've written is slightly more general because it allows a perturbation not necessarily to a nearby thermal state, but to any nearby quantum state. We start with a thermal density matrix, we add some arbitrary perturbation of the density matrix, and then you can show that the change in entanglement entropy for that system is equal to 1 over the temperature times the change in the expectation value of the Hamiltonian. Okay, that's a thing that's true about entropy. We can now imagine that this system is the system that's describing some gravitational system. We can translate that to the gravity side, ask what it means, and it's actually just the thing that Hawking and Bekenstein and others derived in the 70s. So given our dictionary, we just sort of reproduce, starting with the first law of thermodynamics here, we reproduce the black hole area law. The change in, that if I perturb a black hole space-time, that the change in area of the horizon would be related to the change in the mass of the black hole. So that's something we kind of used going into all of this.
But that predates Bekenstein and Hawking because it's classical. I mean, delta area equals 1 over k delta mass is a classical relation. There is no H bar.
Yeah, I may be getting the history wrong, but sometime in the 70s, people worked this out.
It's in the 60s.
Was it 60? Okay.
Okay,
it was before I was born, so okay, but you know what? So all of the developments that we used in this talk came from kind of generalizing to thinking about entropies of subsystems. Okay, so let's see if we can do a similar thing. Can we apply the first law of thermodynamics to subsystems? Okay, well, so it turns out that if you take just the vacuum state of a CFT on a sphere, and then you look at a subsystem, and then you look at the the ensemble that is associated with that subsystem, describes the quantum subsystem. So now, turns out that ensemble is actually a thermal ensemble, just with a different Hamiltonian than the full Hamiltonian for this system. So it turns out that actually I can apply the first law of thermodynamics to constrain how the entropy of a subsystem varies if I start with the vacuum state of a CFT, of one of these systems, and I perturb it a little bit. So I start with a vacuum state, I add a perturbation, which is going to be arbitrary, and then it turns out you can prove that the change in the entropy of this region is related to the change in the energy density inside that region. It's just some integral over the change in the, there should be a delta, over the energy density over that ball with a weighting function. Okay. So it's like the first law in that it relates the change in entropy to the change in energy. Okay. So what happens if I translate that to, so now imagine that I have a geometry that's being encoded by this perturbed thing. Okay, so the original vacuum state was just empty space. Now the perturbation is going to add some perturbation to the metric on top of empty space. But that's constrained somehow by this. And the constraint is that, so this was the surface area that computes this entropy. The change in that surface area when I add the perturbation must equal some other quantity over here on the right-hand side. Turns out that this I can actually also express in terms of entropies, and it's related to, turns out to be related just to the metric of the space-time out near the boundary. Okay, so to summarize that, this constraint translates into a constraint that for any geometry that is encoded in this way, the area of this surface is not independent from the metric out at the boundary. There's some relation between those two things. And now the interesting thing is that, okay, that's one constraint, but I could think of every possible ball-shaped region on this original sphere, and every one of those gives me a similar constraint. Okay. So we get this whole family of kind of non-local constraints that says that if I have a system, if I have a perturbation of empty space, described by this model of quantum gravity, then this metric perturbation is going to be constrained somehow in such a way that the areas of these surfaces are related to the metric at the boundary. And now you can massage, using some mathematics, you can massage that to a much more familiar form. Okay. So it turns out that this set of kind of non-local constraints relating changes in areas of some surfaces to the metric at the boundary, that's basically the integral version of the linearized Einstein equations. So like the integral version of Maxwell's equations, you can massage those into the nice differential version of Maxwell's equations that are local equations. The constraints that you get from these guys can be massaged using Stokes' theorem to the simple constraint that this metric perturbation must satisfy Einstein's equations, linearized about 80 hours. And so we've basically derived directly from some bit of entanglement physics. It's the simplest bit of physics about entropy that you first learned about. That turns into the simplest thing that we would say in Einstein gravity. That's like the Einstein equations about flat space. You can reproduce those, just the weak gravity Einstein's equations.
But these are without immunity, without matter.
Yeah. So far that's without matter, but we can actually extend this. So recently, with these people, we thought about this calculation to the next order. Okay, so starting from a perturbation to the CFT state, either the vacuum, first order perturbation, second order perturbation, we can calculate directly the entanglement entropy of such states. okay, for some very large family of states. And then what we were able to show is that for this large family of states, including the second order perturbations, that actually, number one, you can actually always find a geometry. There's some first plus second order perturbation of ADS that captures that entanglement entropy. And then furthermore, even to the second order, that perturbation must satisfy Einstein's equations. And there you have a matter part of it coming in, and that the matter can be deduced from from one-point functions of various operators in this theory. So a summary of that is that actually let me just emphasize that this is a result that doesn't use any string theory or any of the background. It's a statement about conformal field theories. And the statement is that if I think about a conformal field theory on a sphere in the vacuum state, I think about arbitrary first order perturbations and I calculate the entropy of the state, then those entropies can always be represented by a geometry, and that geometry satisfies Einstein's equations to linear order. And then at second order, there's sort of a somewhat more restricted class of states that we look at, because actually not all states are expected to be dual to classical geometries. But within that class of states, we can extend the result to second order and show that those entropies can always be geometrized, and the geometries satisfy Einstein's equations. Okay, so you get the nonlinear physics of gravity just from asking questions about entanglement entropy in conformal field theories. Okay, so I think it's important to emphasize that that doesn't make any assumptions about string theory and ABSCFT and how it was all derived. So you can see it as kind of a derivation of gravitational physics coming out of quantum field theory. Okay, and then just in the last couple of minutes, I wanted to mention that, well, we can actually learn new things about gravity that we didn't know before. Okay, so we sort of knew that gravitational space-time should satisfy Einstein's equations. That came from looking at one of the very simplest properties of entanglement. But there are all these other fancy properties of entanglement that I didn't know 10 years ago. So what can we learn if we translate those to the gravity side? And so many of these things haven't even been translated yet, but I'll just mention one thing that has. And so this is related to, so the result we're going to get is related to the idea of a positive energy theorem in gravity. So there's a famous positive energy theorem in gravity, and the asymptotically ADS version says that, for any solution of Einstein's equations with reasonable matter, there's a certain definition of energy for a gravitational space-time that you can define, and which is always positive for all these solutions. So that's the positive energy theorem. It's absolutely trivial to understand from this ABSCFT correspondence. So here's the statement on the quantum side. The statement is that every state has an energy that's larger than the vacuum state. Okay, that there is an energy, and that every state has an energy that's larger than the vacuum state. And so if you just translate, if you just say, well, this thing here, we just have to understand what that translates to on the gravity side, and that will give you some quantity which must be positive for all of the possible solutions. Okay. So that was a known thing. But again, we can ask for, is there a subsystem version of that? Now, actually, in quantum theories, you might think that energies of subsystems should also be positive, but actually it's not true in quantum theories. You can have interesting quantum states of field theories where locally you have negative energy, and maybe there's some positive energy somewhere else, and then overall the energy is positive. Okay. So we can't directly claim that there's a local version of the positivity on this side. But what you do have is a statement called the positivity of relative entropy. Okay. And that says that there's a certain energy, there's a certain notion of energy that we can associate to this subsystem. It was actually like this, the same quantity that appeared in the first law. And then if I look at a general state, so that energy doesn't have to be positive relative to the vacuum state. But if I subtract off the entropy, then this combination of things, it's something like a free energy. This combination of things, you can prove in quantum theories it's always positive. So this is known as the positivity of relative entropy in quantum information theory. So it says that basically for every single subsystem I can choose, on the quantum side, there is a positive quantity I can associate to that subsystem. Okay? And now we can ask, what is that on the gravity side? And there was no previously known kind of local version of the positive energy theorem. So this sort of suggests that there should be some positive quantity that you can associate to subsystems of a gravitational system. That result didn't exist. But we were able to just translate this over, say, what this turns into once we apply our dictionary. And then that gave us a definition of an energy that you can define for subsystems of a gravitational system, which are like the interiors of these minimal area surfaces. Okay. So I won't write it down. There's a quantity that we can write down. It's just a classical gravity thing. And now you can go and check that in every normal space-time with reasonable energy, you can calculate that quantity, and you can try to check that it's positive. And I think it should be possible to prove that it's positive using general relativity, but no one's done that yet. Okay, pretty good. So the summary is that, bizarrely, right? We went into this trying to understand quantum gravity, and then there was this new approach that suggested these quantum gravity systems are equivalent to more ordinary quantum systems. And then in trying to understand how that works, what we realized is that the way space-time geometry emerges in that description has fundamentally to do with a very quantum thing, which is the structure of entanglement in your non-gravitational system. Furthermore, if you then look at physics of entanglement, constraints that entanglement entropies for various subsystems, constraints that those things have to obey, and you just translate them over to the gravity side, then you can reproduce some of the most important physics of gravity. So Einstein's equations at perturbative first and second order. And furthermore, we can actually even learn new things about gravitational physics coming from fundamental things that were understood about quantum information theory. So I like to say it's like the ultimate plot twist where you were trying to fit gravity into quantum mechanics, but then it turns out that really, in this perspective, gravity was just a different perspective, different way of looking at a certain quantum system that was quantum all along. So that's all. Yeah.
So I have a more basic question,
Yeah.
which you may or may not want to answer.
Yeah.
It's apparent that the laws of black hole physics are certainly mathematically analogous
Yeah.
to the laws of classical thermodynamics.
Yes.
But there's a great deal of controversy surrounding the black hole information loss paradox. Not all of us
Right.
believe that information is
Right.
preserved.
Right.
Most notably Roger Penrose, for example.
Mm-hmm.
Do you know if there's any real-world evidence that the equations are more than just analogous? Some of us believe that the black hole has zero entropy. So is there real-world evidence
Okay.
that they're more than just mathematically analogous?
So, so it depends what you mean by real world. What I would
Well,
say
they
is
look good
that,
on paper, but like for example, how
Yeah.
do you equate surface gravity to temperature? That's what you're doing
So-
over there.
So yeah, what I would say is, what we had previously was an analogy. You could derive these equations from general relativity. We had no idea why they should follow from, why they had anything to do with actual thermodynamics. Okay, so here the perspective is, I'm going to start with a quantum system. And then what we're starting to be able to show is that the physics of that quantum system, you can alternatively see it as the physics of a gravitational system. From that point of view, you can derive things about the gravitational system. And in particular, we can derive these laws of thermodynamics. So there's sort of a fundamental understanding that if you start with this quantum system, you define a space-time. I mean, maybe you don't care about gravity at all. Maybe you just care about the physics of entanglement of a conformal field theory. But nevertheless, you're going to be led to define this space-time, and that space-time could have black holes. And in that setup, you will derive that those black holes must obey the laws of black hole thermodynamics. And then you might say, well, maybe that's more than just a convenient analogous physical system to understand the physics of conformal field theories. Maybe that's how gravity is actually defined. There are these underlying degrees of freedom. And that would then give you a perspective for why the laws of thermodynamics should be obeyed.
This may be the
We've got
subject.
other people asking
Yeah.
questions.
Yeah, let's-
Oliver, you had one.
Yeah.
Yeah, I actually wanted to ask a bit. I see it's a bit on your slide. So it was about your reconstruction. The talk about your reconstruction of Einstein's equations.
Yeah.
So I was wondering about the all-order claim actually, but I see it's on there. So is there any example of maybe a particular one-parameter family of perturbations of a CFT state, and then you can prove that non-perturbatively that corresponds to exactly satisfying Einstein's equation?
Yeah, I mean, so I mentioned, I wrote this paper, right, there's some work that claims to extend this. I should say that other work makes much stronger assumptions about the ABSCFT correspondence and various details of the correspondence between quantum information quantities and gravity quantities. So if you're willing to accept a bunch of other stuff, which is really very reasonable from the perspective of knowing about ABSCFT, then you can do better. But I guess so far, if you don't want to make any of these extra assumptions, then I'd say what we have is kind of the state of the art at second order.
I mean, there must be some assumptions about the CFT that
Yes.
make it very non-generic.
That's right.
Because otherwise,
Yeah.
Einstein's equations will have huge corrections, even linear
That's right.
Einstein's equations.
Yeah, so
You are looking at a very special conformal field theory.
So this is a good question. So what did I assume something about the conformal field theories? Actually, at first order, the answer is I didn't assume anything. So it just turns out that at first order, if I want to compute the entanglement entropy of the perturbed vacuum state of a CFT, then for all CFTs, there's some perturbation of an ADS metric that captures that entanglement. At second order, to get our results, what we found is that there are two quantities in the CFT that are relevant. One of them is the coefficient that comes into the stress tensor two-point function, and the other one is a coefficient that comes into the entanglement entropy of a ball-shaped region. And if those two numbers are equal, then our second order results work. And if they're not equal, you have to add some higher derivative corrections to the gravity to get them to work. But I think as you go forward, if you follow our approach and go further and further, and you say, what is the entropy at third order or fourth order, then I think you'll get more and more constraints on what your CFT has to be if you want to get just Einstein gravity. If you looked at other CFTs, you would maybe still be able to reproduce the entropies, but using some other theory of gravity.
So let's take one more question, and then we'll have a reception on the 8th floor downstairs.
One of the important measures or things in quantum information is the idea of maximally entangled systems, right?
Yeah.
Has anybody looked into what that looks like in the gravity?
Yeah. Well, so in these systems, maximal. So these are not just fermionic systems. So maximal entanglement would be infinite entanglement in that case. So it's not quite as natural to think about maximally entangled systems. But I think this a close thing is this thermofield double state. So they're the maximally entangled system you can think of as like the infinite temperature limit of two systems that are entangled with each other in this way that I showed on the Maldacena two-sided black hole slide. And so I think that family of states is sort of the analog where you have a large black hole and another large black hole, and then they're geometrically connected behind their horizons. And now you could increase the entanglement, and the black hole gets larger and larger and larger. And so if you thought about a maximally entangled state of these two CFTs, that would kind of be like a state where you had a black hole almost filling up the whole space-time, and then another black hole almost filling up the whole space-time. That would be the thing you would get to if you tried to make maximal entanglement.
Can I ask a question? I think we better move down to perception. Maybe to ask a question.